Thanks, John. So firstly, I'd like to thank John and the other organisers for inviting me here, which to what's been a very interesting 2 weeks. And I'd like to thank all of you for coming out on what's got to be the least attractive talking slot we've had so far, early afternoon on a Friday. So it's great that you've still got your attention for quantum feedback control at this point of the week. In talking with John about what I was going to talk, we agreed that I would give a tutorial talk. And I suppose the main theme that I wanted to get across was to do with what's a really broad applicability for these ideas of quantum trajectories, of what you might call the SLH formalism, to describing real experiments. And that's one of the things that I've found to be very stimulating about this area. And I suppose what I originally, I've changed since I've been here my plan about what I would talk about, because we had at the beginning of last week, and many of you were here for most of that, some really beautiful overview talks about the quantum stochastic differential equations, about measurement and feedback described in this formalism of quantum white noise. And so in terms of this idea of what use are they in physics, I do actually just want to give a bit of a sort of an overview of what people were thinking about in quantum optics, what problems they were trying to solve, and what were some of the highlights there in terms of trying to apply these ideas to physics. And so what I was originally going to talk about was some more recent, the applications of quantum trajectories to more recent experiments in, for example, superconducting circuits, and you're going to hear a lot about those from people who know much more about it than me, either next week or already in this program. So that's what I've decided to do. And so to remind you of the sort of the structure of the theory that we heard about last week, which we'll call the SLH formalism after the papers by James and Goff. So it has these three components, and I've stolen this diagram directly from Matt's talk. One of these components is a description of unitary evolution of a system coupled to its environment, where that environment is treated as a quantum mechanical white noise. And so this is what we heard from about the Hudson-Parasarati quantum stochastic differential equations. And one of the things is that that's if you like, a rigid mathematical structure. If quantum white noise is to make any much sense at all, it's going to look like this, okay? So this describes unitary evolution of both a system, which could be a transmon qubit, a Cooper pair box qubit, or something like this, and its environment, which could be its electromagnetic environment, for example. And then there are various things we might want to do. We might make measurements on the environment. So we might measure that electromagnetic field, and then based on that electromagnetic, on those measurements, we might want to say, what is the quantum mechanical state of the system conditioned on particular measurement results? And we heard about that as this mathematical operation of quantum conditional expectation. And that allows us to write a state of the system, which is, if you like, an estimate or a filtered version of those measurement results. And we get states conditioned on measurement. From there, I could average over those measurement results, and that would give me the quantum master equations, which are very familiar to a wide range of people, and really go back to, I suppose, at least to the Bloch equations, which are very early application of quantum mechanics. On the other hand, I could move directly from this unitary evolution of the system and environment and take, if you like, a quantum mechanical average, the partial trace over the environmental variables, and obtain this same quantum master equation. So it really doesn't matter what I measure on the environment. I'm going to get the same dynamics for the system alone if I forget about the results of those measurements, or if I don't perform them at all. Okay. And so what we saw was that this is a very nice theory. It's got the appropriate sense of unitary evolution. There's a very nice sense of what quantum conditional expectation should look like, quantum filtering due to Belavkin, and then these master equations, Pauli, Bloch, and so on and so forth. And so the point I'd like to make here is that this is not in physics what we're going to start with. Okay, these are going to be approximate descriptions of physical systems that arise in nature. Okay, and what's of quite a lot of interest to me is that this theoretical framework has been very effective in describing real experiments, particularly in quantum optics, but increasingly these days, I would say, in circuit QED, in microwave applications, and in optomechanics. It's relevant to physics in some regime of the models, which we'll talk about, and it tends to be very, very accurate in quantum optics, where the Q's of the relevant resonances, whether it's the spontaneous emission rate of an atom over its energy level splitting, or whether it's the Q of an optical Fabry-Perot cavity, those numbers tend to be very, very large. And worrying about the distinction between the underlying model and this quantum Brownian motion approximation is fruitless. If I'm going to apply this to oscillators that are in the megahertz regime, that are in the gigahertz regime, and have only moderate Q, one might ask, well, how accurate is this? So I want to talk a little bit. So in physics, this understanding of the fact that quantum mechanical models approach quantum Brownian motion, quantum stochastic differential equations in the sense of Hudson and Pastorati, goes back to Gardner and Collett, who were mentioned quite a lot. So I want to talk a little bit about what they were doing. And they were thinking about a system that I want to sort of imagine abstractly like this. Okay, so this diagram could represent, here the circle could be a Cooper pair box qubit, so an effective two-level system that is some superconducting Josephson junction device, and it's sitting, these two lines are supposed to indicate some planar transmission line. So it's sitting in a plane, microwaves come down here, they can reflect off the device back this way, now they can be transmitted past the device, and this device is going to radiate both in this direction and in that direction. And if you just use your classical sense of Maxwell's equations, you can imagine that here there's some possibility for this drive field to be directly reflected, some possibility for it to be transmitted. There's some interference between the just forward scattered light that effectively doesn't touch the two-level atom at all, and the light that is the dipole radiation that is radiated by the atom. So any quantum mechanical treatment of this situation needs to account properly for the interference between light that's directly transmitted past the system and light that's emitted by, it could be an optical cavity. So specifically, Gardner and Collett were thinking about things called optical parametric amplifiers, which are just optical Fabry-Perot cavities with nonlinear crystals inside them. It could be resonance fluorescence of a single ion in free space, in which case you need to think of this transmission line as being every possible direction that light could be shining on that atom. It could be in the modern setting a superconducting circuit. But whatever we're doing, if we've got a proper quantum mechanical treatment, we better be treating the interference of the light that's just directly transmitted past and the light that's radiated by the system of interest. So what was happening in quantum optics at the time that Gardner and Collett were working is that people were very, very confused about this sort of problem in the situation where you were thinking about optical parametric amplifiers. So in this case, this was a laser beam. These were two mirrors with a nonlinear crystal inside. And then I could think about, for example, let's in fact simplify the, imagine that one of the mirrors is nearly perfect so that all the light is just radiated back, or well, actually, no, sorry. Let's just think about this thing. So let's just think about the light that's transmitted through, and at the end of this line, I'm going to do homodyne detection. And so that homodyne detection is going to measure some quadrature of the transmitted light. And the question really was, could the fluctuations in that homodyne photocurrent be made arbitrarily small? Okay, and there were various calculations. Okay, so Jared Milburn, who's been here, had done a calculation in which he showed that if you thought about the quadrature of the light inside the optical cavity that corresponded to the quadrature that you were going to measure outside, that the fluctuations in that could be no less than half the fluctuations in the vacuum. Okay? So if I just look at the steady state of the field in the single mode inside the cavity, it would have at least half as much fluctuations as in a vacuum field. Okay? So in the quantum optical parlance, it could be squeezed, but not by very much. Okay? There were other calculations that people like Horace Ewan had been involved in, but there were a range of people. And those calculations sort of thought more in free space, sort of thought about free space fields flowing past some nonlinear crystal. And it appeared in those calculations that the fluctuations in the quadrature of the free field sort of far away from the nonlinear crystal could be arbitrarily narrow, could be arbitrarily small, could be highly squeezed. And so what was happening was the fluctuations in one quadrature are growing very greatly, the fluctuations in the other quadrature are decreasing, the product of those fluctuations is such that Heisenberg uncertainty is satisfied. So they suggested that you could use an optical parametric amplifier or an optical parametric effect of some kind to achieve arbitrarily large amounts of squeezing. Okay? And as I understand it, there was quite a lot of argy-bargy, okay, between exactly who was right about this and what an experiment would actually detect if you put a homodyne detector at the end of this thing and actually measured the fluctuations. And experiments that weren't at that time possible. So it turns out, I suppose, unsurprisingly, that both sets of authors were correct. Okay? So there was nothing wrong with Jared's calculation, which indicated that the fluctuations inside the cavity were at least half as large as the fluctuations of the vacuum. But there was also nothing wrong with the conclusion that a detector far from the cavity would see arbitrarily large squeezing. And the reason, and so the theoretical apparatus that Gardner and Collett wrote down, what they pointed out was that you really have to worry about the fact that incident on this cavity, this drive, I've said, it could be vacuum. Okay? And you need to think about the vacuum as a non-trivial signal that's approaching here. And there is going to be an interference between the vacuum that's incident on the cavity and the light that's radiated by the cavity. And as I was saying, any serious calculation's got to take that into account. And they wrote down what they called the input-output theory, and they showed that if you really did that properly, and this was Collett's master's thesis, then indeed in the output field there could be very large squeezing, despite the fact that inside the cavity there wasn't very large squeezing. And actually in the first paper, they used mathematical equations which are basically variants of Langevin equations. And Langevin equations went back at least to the 60s in quantum optics, where they were sort of written down as phenomenological models of open quantum systems. And so the thing that Collett was able to do was to relate the Langevin white noise, which was input to the dynamics of the quantum optical system, to the appropriate fields that were measured a long way away. And this was the relationship which they called the input-output relation. And if you read their first paper, there aren't any quantum stochastic differential equations, and there's a lot of language that really comes from scattering theory. So they're sort of thinking in terms of scattering theory. So the notion that you're shining in a field from a long way away, it's interacting with some scatterer, and then if you're going to have a detector, it's also a long way away from the sample. And a lot of the techniques they were doing, I think they were in some way motivated by a knowledge of scattering theory. And then in their second longer paper, they've read the paper of Hudson and Parasarati, which had appeared around about the same time. And so they recognize that the system that they're interested in is going to approach a quantum stochastic differential equation in an appropriate limit.
When you say they were both right, was it because there were experiments that confirmed both somewhat separately, or that they found a theoretical framework that made them both right?
So what I mean that they were both right in the sense that inside the cavity there really is only half as much squeeze. The squeezing factor is really a half,
Yeah.
and outside the cavity, if you place a detector, you really can get as much squeezing as you like.
So that this was a theory, people came to terms with this theoretically.
So people came to terms with this theoretically. Now, in that discussion, there would have been some confusion, and I suspect it was implicit in the way people were talking about this calculation of the intracavity fluctuations, that they would also be the fluctuations seen by the detector. And anyone who said that was, of course, wrong. Okay? So in order to work out the fluctuations seen by the detector, you needed to take account of the destructive interference between the incident vacuum and the radiated light from the cavity field. So in that sense, someone who said that, someone who inferred from the intracavity fluctuations to that's wrong. But the calculation that said what does the field look like inside the cavity was perfectly fine. and these other calculational methods, which didn't really correspond to input-output theory, but they did correctly predict what you would see in a homodyne detection.
Is there in this kind of in own discussion does the bandwidth, of the pulse with respect to bandwidth of the cavity, does it come through at some point at all, or is it at all important how long your pulse is with respect to the cavity's bandwidth or not?
Sorry, you're saying if you're saying if the pulse were very, very short,
or vice versa, is very long. The limit of CW drive, for example, if you have a continuous drive, is this still true that we can have as much squeezing as we want on the other side?
Yeah. So what this calculation? So I should have actually put a plot. So I should have gotten a plot from Gardner and Collett's theory. So in this case, there's a drive on the nonlinear crystal, which is at twice the frequency where you see the squeezing. But you can think at the frequency where you see the squeezing, you can write down an effective model where the Hamiltonian's a squared plus a dagger squared. And in that case, you can think that the drive is just the vacuum. And yes, it can be CW, it's as long as you like. And then you can say, well, if I looked at the quadrature fluctuations at a given frequency, how much noise reduction would I see? And what you see is a spectrum of noise reduction that's Lorentzian, and it has the width of the cavity. So you're going to squeeze the fluctuations about the central frequency, which is the frequency of the cavity, and the bandwidth of that squeezing is going to be the cavity line width. And so there's some white noise. So what's going to come out is not going to be broadband squeezing unless you make the cavity decay rate very rapid and thereby squeeze a broad band.
Okay, that's in the CW.
That's in the CW regime. Yeah. So that's how the CW regime works. That's what they were actually interested in. That's, if you see the figures in there, which I should have put in, the figures in their plots are these Lorentzians. Yeah. And then, so I should note that in a typical experiment, what you actually do is you look at the squeezing off to the side of that frequency. So in optical experiments, the mirrors move, and low frequency motions of the mirrors means that very close to the resonance frequency, you don't see squeezing at all. And so there's a lot of trick in terms of how close to the resonance frequency can you observe squeezing. The early experiments were detuned by maybe 10, well, quite a bit. I'm going to get the order of magnitude wrong, so I won't say anything. But, they might have been several megahertz, and you might have detuned by 100 kilohertz or something like this. So I just want to give us a concrete example here of what this sort of model looks like. And so this example is one where I'm thinking about a Cooper pair box, which I'm treating in a two-level approximation coupled to a transmission line. And in that case, I can write down just the classical model of Maxwell's equations and the physics of Josephson junctions, and I can do canonical quantization on that model, and I can end up with a Hamiltonian. Now, Hamiltonian looks like this. Okay, so there are left-moving and right-moving modes of the electromagnetic field in this. I've missed something off. There are left-moving and right-moving modes of the electromagnetic field in this cavity. And the photons, they have a range of frequencies omega, and the energy for each frequency is h bar omega. So there's a factor out the front there. There's h bar, and there's an omega inside the integral. And so this is just the free field of the free field of the transmission line. The qubit, I'm imagining that's a Cooper pair box qubit, and that we're very close to charge degeneracy. So in that case, the qubit levels, the up and down state, are split by the Josephson energy of the junction. Doesn't matter what this is, but there's some energy that the two-level system has. And then for this qubit, the X eigenstates, so the Z eigenstates are superpositions of numbers of Cooper pairs on the island. So the X eigenstates are actually the number of Cooper pairs on the island. And so the number of Cooper pairs that are in equilibrium on the island depends on the voltage, their potential, or electric potential on the superconducting island of the Cooper pair box. And so here I've written, so as the electromagnetic field here vibrates, the voltage on that island is going to oscillate. So here's the voltage at the location, I just set x equal to 0, corresponding to the location of the Cooper pair box. And so what's the energy associated with that? Well, it's going to be E. I suppose I should have written 2E because the difference in charge between the two is a Cooper pair, so it's 2 electrons. What matters is the sum, if you think of the island of this like an island of superconductor, there's some capacitance to the transmission line, which I've called CG, and then there are other bits of metal and charges around the place, and so the total capacitance that couples this island to surrounding things is C sigma, and so there's some ratio that describes how much charge on the Cooper pair box talks to its environment, and so here's the coupling Hamiltonian. And I just want to do this because I want to say, we can write down a physical model with concrete physical parameters, and it looks like this, okay? So this voltage, when you do canonical quantization of the transmission line, the voltage operator just looks like some sum. It's just some linear combination of raising and lowering for the modes that are left and right moving along the cavity. So this is really a concrete model. It's got physics things in it, like ZC here is the impedance of the transmission line. Okay, so this is an example of the sort of model that you start with that in a limit of weak coupling here is going to look like a quantum stochastic differential equation. Now I'm sorry about these. These look beautiful on my computer, and I'm sorry that it looks. So I just want to do one small manipulation of this model in order to indicate something about the Markov approximation. And so that is just to go into the interaction picture. So I'm going to go into the interaction picture with respect to the qubit Hamiltonian and with respect to the free field Hamiltonian of the transmission line. When I do that, I'm going to let omega naught be Ej over h bar. That's the Bohr frequency of the qubit. So what's going to happen is that the qubit raising operator and the qubit lowering operator are going to pick up phase factors, in the case of the lowering operator, like e to the minus I omega naught t, and in the case of the raising operator, like e to the I omega naught t. Likewise, the raising and lowering operators of the modes of the transmission line, the lowering operators are going to pick e to the minus I omega t, where omega is the frequency of the mode, and the raising operator is going to pick e to the I omega t, where that's the frequency of the mode. And so what we get here is this Hamiltonian. Okay, so that's what I'm going to say. What you'll notice is that there are linear combinations here, or there's an integral over frequency. So there's a linear combination of the Bath modes, of the modes of the transmission line, that's a function of t, that describes the interaction picture Hamiltonian. So a schematic way of writing this Hamiltonian is it looks like a system operator, sigma dagger or sigma, multiplied by a particular combination of modes that is labeled by time. Okay? And the picture that you might want to have of this is that this particular thing, which I've called b in of t right going, so that's just the integral here of the omega of, there's a square root of omega factor that comes from the previous slide, b omega right going times these phase factors, that thing, b in of t, is somehow a mode of the electromagnetic field that's going to interact with the system at time t. That's true in the sense that it is exactly the coefficient of sigma dagger in the interaction picture. Okay. And I've just missed off some counter-rotating terms, so let's not worry about them. I've also rejigged some of these coefficients. I'll come back to that in a minute. Okay, so the picture of the Markov approximation of when it's valid, okay, is that if the story I just told you, that I want to think about this as modes of the electromagnetic field interacting with the system and then propagating away, if that's true, then it really, operators, input operators at different times should commute, okay? And I just note that this is a confusing thing about the notation in all these quantum optics papers, that you get these things called b in of t, and people, you might think that that's interaction picture time evolution, and it's sort of not. It's a label describing the time at which this mode is going to interact with the system. Okay, what happens is it's easy enough, given these definitions, to compute the commutator of these two things. Okay, you do this commutation. So what I've done here is there's these B's and B daggers. They're just conventional field modes. They have delta function interactions, delta function commutation relations. So when I do that, I can get rid of one of these integrals, and I get this thing here, okay? And if you look at it with one eye, that thing looks like a delta function, okay? So for some purposes, this thing here looks a bit like a delta function, okay? So there is some limit, and it's going to be a limit of a high Q resonance in which these fields here are sort of close enough, if you like, to being commuting, and so I can really think of them as independent modes interacting with the system and then propagating away. Okay, and so what Gardner and Collett did is they basically gave some arguments about a regime in which that was somehow true. And they talk about in their paper about the Markov rotating wave approximation. They do some second-order perturbation theory calculation, and then they end up with operator Langevin equations, which you can think of as Ito Langevin equations that we've talked about, and they get master equations. And importantly, they say, well, what happens to the input of the electromagnetic field? So what happens to those B-in operators after they've interacted with the system? So the physics of it is that the input field is going to interact with the system, is going to reflect away, and that's what's going to be available to a detector at later times. And so you just want to propagate the input field forward in time using the same unitary interaction that's describing the interaction of the system and the field in order to get the output field. Okay? And this formula here, which relates the output field to the input field and some system operator, conceptually this has two terms, one of which is just direct transmission from the input to the output, and one of which is radiation from the system. Okay? So this term here is what's being radiated by the qubit. So this is what Gardner and Collett wrote down, and they used this formula in order to correctly calculate the correlation functions which are appropriate for homodome detection to work out the spectrum that I described earlier. Okay, in this equation, so what you end up with in terms of this parameter lambda, which was describing the weak coupling on the previous slide, this spontaneous emission rate that we've obtained is just lambda squared. Okay, so it's somehow second order perturbation theory that we've obtained. And so they wrote this down. Now, I don't think you could argue that they derived this, but they make arguments that what you end up with in this case is a quantum stochastic differential equation. And the limit is the limit where this decay rate gamma is much less than the qubits level splitting omega naught. Okay, so if the Q of this resonance is omega naught over gamma, you want the Q to be large in order for this theory to correspond that closely to the original model.
What's the significance of T plus?
What happens is that, so really in all earlier formulas it's just T. I'm just emphasizing that what happens to these input fields is they're freely propagating. They interact with the system at time T, then they propagate away. So if I were to propagate forward in time at any time later, I would get the same answer. And conceptually, it's just got to be after. I just mean that, that there's an instant, it's thinking very loosely, there's an instant at which they relate, that they interact, and this will be the output operator at any later time after that. Yeah, so I just want to emphasize that it's any time after the time at which it interacts. But indeed, if you define everything formally, you get to write down U of T. And so in formulae that you've seen in other earlier talks in this, people just write U of T.
I would just comment that one of the things that I found of note when I started learning the microwave version of this after I grew up with this quantum optics one is actually this equation that you've written down in the microwave literature is always derived first classically.
Right.
And then you do the quantization, and then you get this thing.
Yeah.
So it seemed, whereas in the quantum optics tradition, this only appears after a lot of work and a lot of approximations and a lot of quantumness, so it seems kind of more spooky than it really is. But you can basically get this just from finding the boundary conditions for a transmission line using classical equations.
And yeah, I think that's a really important point. I wanted to say at the beginning when I introduced, so I was talking earlier and sort of informally about saying use your classical Maxwell's equation intuition about this system in the transmission line. I mean, a competent, this is an important point. Like if you think literally about this transmission line version, none of this is very surprising. It's really just the natural quantization. Yeah. Okay, so okay, so that's what we want. Okay, so I think I've said everything I want to about all of this. Okay, so I just want to say here, so you could ask, is there a mathematical result corresponding to what Gardner and Collett said? So one paper which does something like this which has a precise statement starting from the Hamiltonian I wrote down, or actually a slightly more general one, and saying, well, here is a quantum stochastic differential equation which describes that unitary evolution in some limit. There may be many other papers, but so this is one that I read recently because it came on the archive recently, but it's an ancient paper, as John was telling me last week. And so the basic idea there is that you take some limit called the Van Hove limit, in which you imagine that the coupling, lambda, between the system and the transmission line gets small, and you rescale time in that limit. So t goes to something like t over lambda squared. So if my units are confusing, remember lambda is like the square root of a frequency. Lambda squared, here this is just the spontaneous emission rate of the atom inside the transmission line. So what this is saying is I'm going to get something that's going to agree that this limit means that times that are finite are times of order the decay rate of the atom, not times of order 1 over omega naught that are the oscillation period of the qubit.
So lambda is the coupling between the driving field of the system or the system?
I'm just going to go back. So when I rewrote this coupling in terms of the input fields, I left this one thing lambda. Okay, it's a square root of a rate because these input fields have delta function correlation, so they're like the square root of a rate too. And it's just going to be easier to compare to other things. Okay, so one thing I would say is that this vagueness about timescales of order 1 over omega naught, that's in any physics discussion as well. If you've ever made a rotating wave approximation, that rotating wave approximation is like averaging over a time omega naught, where omega naught is the oscillation frequency. Okay, so when we throw away counter-rotating terms ever, it's one way of justifying that approximation would be to say that I'm interested in states averaged over an oscillation period. And there's a name for that in dynamical systems theory, averaging theory. Okay, so one thing I want to point out about these master equations is they're a little bit vague about what time this density matrix is at. Right? I can inquire about times of order 1 over the times long enough that they're of order 1 over the spontaneous emission rate, and that's evident in this theory. And so what these guys show is that if you take matrix elements of the unitary evolution of the full model, matrix elements of the evolution equations of the quantum stochastic differential equation, they approach each other in this limit. Okay, so that's sort of a rigorous version of that thing. Okay, and I'm going to skip over that. So there's I learned from papers by Michel Devereux a beautiful way to relate this Q of this oscillator to the fine structure constant. This ratio which describes the capacitive coupling, and this ratio which describes the impedance of the transmission line relative to the impedance of free space. Okay, so for this theory to apply, the Q needs to be large. That means this ratio needs to be small. Thankfully, this is something that sort of wants to be small because this is 1 over 137. But okay, that's for people who are interested in. Sorry. Z0 is the.
No,
it's less than 1. Yeah, thank you. Yeah. Okay, so in quantum optics, people have developed this kind of input-output theory. It saw many applications to quantum optical systems. But that's, if you like, the top of Matt James's diagram. It doesn't describe what I think is the most interesting and sort of unique aspect of this theory, which is the state conditioned on measurement. Okay. So people in quantum optics thought about that also. And here, actually, they were aware of the mathematical physics literature a bit later in the piece than really in the case of Gardner and Collett. And so I don't know who's had this experience, but certainly people who taught me quantum mechanics were fond of saying something like, quantum mechanics is a statistical theory. It can't say anything about the results of measurements on individual quantum mechanical systems. Right? So I don't know if any of you have had the experience of someone telling you that, but people told me that. Okay? And I think that's indicative of the fact that physicists were somehow by training deeply confused about statistics. Okay? So anyway, here is an example which this is Schrodinger in 1952, This is quoted in Plenio and Knight's review of trajectory theory, which is in RevModPhys, and which is very interesting on this history of where the trajectory theories came from. And so I think if you read this, there are two elements that he's saying. The first is he just can't conceive of an experiment in which you get signal to noise greater than 1 on measurements of a single quantum system, like a single electron, a single two-level atom, a single photon. Okay? So that's sort of in this quote. And the other aspect of it is somehow the idea that it's a statistical theory and we can only talk about averages. And so I think that that was an obstacle that people had to overcome in order to think about states conditioned on measurement. And in the mid-80s, in quantum optics, an experimental system that was very important in people writing down trajectory theories was what's called the electron shelving effect. Okay? And so this had been proposed by Damelt in the mid-70s. And he said, imagine I could look at the fluorescence from a single ion trapped in free space. Okay? And imagine that that ion had, roughly speaking, think of these as two ground states. Okay? So there are two states, 0 and 1. And this should be a big, thick line. This is a laser drive that drives 0 to 1, and then there's an emission from 1 to 0, and it goes back and forth very, very rapidly. But this 2 is metastable. So if I get into 2, the decay back to 0 is very, very slow. Okay? So I can shine a very intense laser on here, okay? And I'll get a lot of fluorescence until this process, which is slow, drives me into 2, and then I'm stuck. Okay? So you could think of this as a quantum measurement. Right? If you prepare initially a superposition of 0 and 2, you shine on the laser and you see fluorescence, you've projected onto 0. If you shine on the laser and you don't see fluorescence, you've projected onto 2. Okay? And so in the mid-80s, it became possible to implement this experiment. Okay? And I'm actually very disappointed in the ion trapping community. I could not find on YouTube a video of this. Right? It should be the case that there's a YouTube picture of a single ion flashing. You can look through an objective, a microscope, and you can watch this yourself. We could all perform quantum measurement right here, okay? So there were these experiments, and theorists could be taken into the lab, and they could see, here's a bright period, here's a dark period, here's a bright period, dark period, and that is a single valence electron on a single ion hopping between two different states, okay? So it's single-shot quantum measurement. And I think it was pretty much, as far as I know, that's sort of the first time someone could do single-shot quantum measurement. Okay, and it's kind of deeply shocking if you think that you can't predict the results of measurements on single quantum systems because you're there looking with your naked eye at what a single valence electron is doing. Okay, and so it's pretty clear that there should be a theoretical apparatus that calculates, for example, the average time I live in that state. Right. The average time I live in this state, right? This process is not quite a random telegraph signal, but in some limits it approaches a random telegraph signal. And the average, stay time in the one state or the other, that's calculable quite clearly, okay? And not only that, if I see a bright spot, I should be able to conclude that I'm in one of these two states. And if I see a dark spot, I should be able to conclude that I'm in that state, okay? So as well as calculating the statistics of the bright and dark periods, I should be able to say, what is the quantum system doing based on the results of the detector that I'm looking at? Right? The detector could just be my eye looking through a lens. Right? Okay, so what happened was that a theory which actually just had input-output theory or just had master equations was not readily able to do this. Okay? And so it was pretty clear task to calculate statistics of bright and dark periods, the state conditioned on this thing. And so there's a series of papers that amounted, around about this period in the very early 90s, quantum opticians began to write down quantum trajectory equations, so Belavkin filtering equations for quantum states conditioned on photo detection and on homodyne detection. Okay, so historically, Carmichael and Wiseman and Milburn obtained the homodyne detection equations by effectively considering a limit of photon counting trajectories. So mostly because in this experiment I just showed you, it's a photon counting detector or an intensity detector that was of interest. That's what people were sort of focused on. Okay? And so if you read the review by Plenio and Knight, they give a good account of the sort of sequence of events, of conferences people attended, of arguments that were taking place about what meaning I could ascribe to a state of an individual quantum system conditioned on detector results. Okay? And I'll just mention that, so there's an early sort of group of papers I've picked the ones that I feel are sort of most significant. These papers are attempting to calculate roughly this first problem. What are the statistics of bright and dark periods? And what can I say about the statistics of photon counts from a single system, beginning with Cook and Kimball, who were just directly thinking about that electron shelving experiment. These two papers here by Kontinuji and Dalibar and Zolamata and Walls, they were really trying to get at the statistics of more general systems and what they were calling exclusive probabilities of photon counts. So if I specify the times at which my detector is going to click, I want to know what the probability of that is with the specification that there weren't any clicks at intervening times. So it turns out that the correlation functions that quantum opticians most easily knew how to calculate from input-output theory and master equations would tell you, roughly speaking, what's the probability of your detector going click at times t1, t2, and t3, averaged over whether or not there were clicks at any other times. That's the G2 functions and the G1 functions. So these exclusive probability, exclusive photon detection probabilities, where the detector goes click, then it's dark, then it goes click, then it goes dark. That's what's being calculated in these three papers, and that's what people are using to understand this sort of thing. Okay, and this paper here, they've actually read a paper by Srinivas and Davies about generalized measurements, and they're using that. But none of these people have read Belavkin. Okay, but Belavkin's starting to write around this time. And then there's this later thing where people are saying, right, given that my detector goes click, I want to ascribe a quantum state to the system. Okay, but often the motivation for these authors is actually to have simulations of density matrices using pure states. So if the density matrix is d squared dimensional, the pure state is dimension d, I might be able to simulate a larger system by randomly propagating pure states. And so if you read some of these papers, particularly this one, for example, this notion that the states in quantum trajectories are states conditioned on measurement results is quite hidden. Okay? But Carmichael, for example, and Wiseman and Milburn, they're really clearly thinking about states conditioned on measurement. Okay, and in this paper, I actually particularly like this paper. This paper here describes the derivation of what we would call now a Belavkin filtering equation for, I think, actually pretty much homodyne detection as well as photon counting. And it's written in the language of quantum stochastic differential equations. Some of the derivations may not be perfectly clear, but it's a nice paper. That's in Physical Review A in 1992. And I think in this paper you'll see that they have read some subset of papers by Bacciali and Belavkin. So this mathematical physics literature. But essentially familiarity with that mathematical physics literature is not very widespread in the quantum optics community until quite a bit later. Okay. I'm not doing too badly. Okay, so for hopefully I've sort of just want to emphasize what the picture is that we've come to. Okay, so the idea is that in this Markov limit, in which the input fields at different times roughly commute, we should be roughly speaking allowed to think that our system that's radiating, say the Cooper pair box in the transmission line, is interacting with a series of modes of the transmission line that interact sequentially, that move away, and that then are detected. And this interaction here is unitary. There's a state describing the whole thing, and when I make a measurement here, which could be photon counting, which could be homodyne detection, when I make that measurement, it's perfectly legal to write down a state conditioned on the result of that measurement. And here I've just written, I think correctly, the photon counting trajectory. So that, and I think something that this theory has going for it is it's had a lot of applications. So it's had applications to simulating master equations for these systems, but it's very versatile. It's possible to put in a lot of experimental imperfections, like detection and bad detection quantum efficiency. It's possible to describe feedback. It's possible to describe finite detector bandwidth. It's possible to describe finite feedback bandwidth. So you really can go away. This is this beautiful experiment of the Siddiqui group thinking about feedback stabilization of Rabi oscillations. And you can really go away, and I'm sorry again about this thing, but you can really compare theory and experiment on the same line, and everything really agrees. Okay, so it's a really flexible thing that can be applied in many places. Okay, so that was That's sort of what I wanted to emphasize, but it's valid in this limit where you've got a high Q. Now, I just want to say, I just want to mention that, a lot of physicists, so I've been talking to condensed matter physicists a bit more recently than quantum opticians, and I would say it's fair to say a lot of them are quite allergic to the approximations that I described, this kind of Markov approximation. And one reason to be allergic to it is that it's an uncontrolled approximation in the sense that we don't know systematically how to improve it. Okay? It seems a bit as though it's all or nothing. Okay? And you'll find in the literature, many people thinking about what should non-Markovian trajectories look like. That's the trajectories that somehow or other account for, something more complicated happening in the bar. In fact, if you're talking about Matt's diagram previously, the bit that describes the state of the open quantum system and the bit that describes this open quantum system and its environment, there are actually many alternative approaches to treating that. Okay, so there's Kaldish formalism for doing Feynman diagrams. There's Feynman-Vernon path integral formalisms, at least in principle in those approaches, you don't have to make approximations corresponding to the Markov approximation, rotating wave approximation, and so on. At least in principle, those are systematically improvable techniques. Okay? And so, the thing that I think is really useful for this community and a beautiful theoretical tool is this idea of trajectories, of states conditioned on measurement. Okay? And that's sort of, if you like, the unique contribution of this community of mathematical physics and also quantum optics as a tool to thinking about this sort of system in physics. But it would be very nice if we actually understood how to systematically improve this notion of a filter in a situation where the interaction between the system and the environment is to some extent non-Markovian. The more you think about, for example, as Jake was pointing out at the beginning of last week, if you've got optomechanical systems with megahertz frequencies and not very high Qs, then that's something. It's sort of clear that that's something you might want to have. Okay, so I just want to tell you about some of my prejudices about this. The first one is my prejudice is that this theory is actually very useful and actually is probably applicable quite widely, even for Qs that are moderate. Okay? At least, for example, if you're talking about frequencies close to the resonance. Okay? So even for moderate Qs, if you're close to the resonance, things look roughly Lorentzian. Okay? But that it would be useful to use some idea about these alternative approaches in order to help understand how to proceed. Okay? And I just want to point out two aspects of this literature on more sophisticated approaches. Okay, so the precise model that I wrote down of the transmission line coupled to a two-level system is isomorphic to something called the anisotropic Kondo problem, which is a problem condensed matter physicists have studied using a very wide array of sophisticated techniques. In particular, it's actually an integral system which can be solved by the Bethe-Ansatz approach. For example, there's, and Shanwei Fan has been writing papers about this in recent times, and there are a number of PRLs. But I actually really like this paper here, which was in Physics Letters, but it's on the archive, and it's from about 1997. And they apply techniques that they've been developing to do the Bethe-Ansatz solution of the precise model that I was talking about. They apply that to quantum optics and actually go to the effort of saying, here's an explicit quantum optical model of an atom coupled to, basically a transmission line. And here's what our sort of theory says about it. Okay? And so they derive from an expansion. It's a beautiful theoretical picture of waves which are a bit like solitons propagating along the transmission line and then reflecting off. They can do an expansion in these solitons. And the lowest order expansion in that soliton gives them this result, right? So this is a result which tells us how does the Q of the atom, so the spontaneous emission rate over its frequency, depend on this parameter lambda, okay? So G is just lambda squared, okay? So this is just giving us, an explicit, non-perturbative expression for the Q, okay? So what they show is that the atom has a resonance. That resonance is Lorentzian near to its central frequency, that the width of that Lorentzian is given by this formula. Okay? And so the picture I get from that is, well, I could presumably fit a trajectory theory to this sort of theory with, they say this G parameter could be as large as 1/5 for this thing to apply. I could fit a trajectory theory to this. What I should just be aware of is the dependence of the Q on the underlying parameter lambda could be different from what I thought, but I probably don't care about that very much. Okay, so that would be a picture in which the detector. I actually want to go back. That would be a picture in which the detector here is located a fair distance away from the system, and at the detector functions the same way it always did. Little packets of light come up and it will click or not click, or it will detect a homodyne detection in some broadband or not. Okay? And I could construct here fields labeled by the time t at which the field strikes the detector, which roughly commute. Okay? And I could have a trajectory. It's just that the time t at which the field strikes the detector will not be precisely the time at which the interaction with the system occurred. That the interaction time with the system is going to have actually have to be averaged over a memory time, which could get to be longer and longer. Okay? And the requirement is going to be that the detector is more than the propagation frequency of light away from the system. Okay? And in that limit, I should be able to ascribe a system state based on these detector clicks, which is averaged over a time scale, which will get longer and longer as I make the Q smaller and smaller. Okay? You might object that while I want to know the quantum state at a particular time, I don't want to know it over this vague time average, but I would argue that if you write down a trajectory today, you are already averaging at least over an optical period. So you've made the rotating wave approximation, or you've taken this Van Hove limit, and you've actually not committing to at what time does, the state in a trajectory theory doesn't have a definite time. It basically, it's within some number of optical periods of that time. Okay? So I would argue that we're already doing that. Okay? And there should be some fairly straightforward way of writing down conditioned states that have progressively less certain times, right? That are averaged over, if you like, longer and longer periods. Okay, so I just want to point that out. Those of you who are interested in that, there's a number of papers I'll just point out. There's Karen Leher has a nice paper about Kondo physics in microwave, something like the Kondo physics of microwaves or something like this. And so she's considering basically the same model that I wrote down in a limit where the Q is not large. There's Doherty, Glassman, and two other collaborators have a very nice paper about transmission line, a line of Josephson junction devices with a defect in which they derive exactly the same model that I already described, and it's easy to get into a limit where the Q is not large. There are others. There are other instances of people thinking about this physics, but both of those are places to learn about some of the tools that condensed matter physicists have used to study this sort of system. Yeah, okay. That's everything I wanted to say. Thanks very much.
Can I put the condensed matter point of view? I mean, certainly at the time, sort of the late 80s, early 90s, people in condensed matter were thinking about these things.
Yeah.
I mean, the people you haven't mentioned, people like Diossi, Percival, even Garani, Rumi, and Weber. But actually, it goes back a bit further than that. I think Slava Balavkin clearly did the vast majority of the work before everybody knew about it. But certainly, sort of motivated by the macroscopic quantum tunneling work, Clark, Cleland, Devereux in the early days. There were people, particularly theorists, looking at things like not individual trajectories as such, but individual trajectories in the way of calculating averages for those sorts of systems. I mean, the ones I'm thinking about, Tim Spiller did quite a lot of this, but also what I'm thinking of is Dickman did quite a lot of work in Lancaster on sort of quantizing path integrals and calculating semi-classical actions for sort of wells and things like that.
There's a guy called Minsky as well who does that. You restrict the range of the path integral.
So there was an awful lot of that work, but at the time, we were very much motivated by that quote from Schrödinger that I had in the back of my head. It was Bohr that said that, but I think you're probably right.
Well, Martin and Peter say it's Schrödinger. Yeah.
I think Bohr said something similar. Actually.
Yeah, I suspect people. Yeah, many people must have said similar.
Certainly at the time, I mean, there were sort of two distinct communities. I mean, people like Peter Knight were probably one of the some of the few that actually sat in both camps.
Yeah.
And I remember when I went down to New Zealand, I was asked by Ian Percival to sort out that guy Wiseman. Because Howard had given him some grief over some of the claims and some of the touristic.
Yeah, I remember that. Right, that's right. So yeah, so the first tranche of people you mentioned are people that are important in that they really wrote down the same equations, these same trajectory equations, for a range of motivations, but definitely wrote those things down. A lot of them were thinking about sort of alternatives to quantum mechanics, so Pearl anyway, Doherty, Romani, and Weber, and they're in this Rev Mod Phys at some point. But I think it's a good point that there's this condensed matter literature of people thinking about decoherence in superconducting circuits. And I mentioned at some point here, there's a Leggett and a cast of thousands have a Rev Mod Phys from the mid-80s. That's Garg and Matthew Fisher is on it. A lot of people on it. And so if the people in that community tend to think, what are these guys still talking about open quantum systems? Anything you want to know is in that, and there's a lot of stuff in that review, including there's a wide range of techniques that would pay for people to be aware of. Yeah.
About this discussion of Markovian limit, it seems to me that I don't have a feeling that it should at all depend on the Q with respect to on the Q of the system in some sense, because you see, this is somehow actually much more related to the environment. How the noise, essentially the noise path, which doesn't depend on the system by itself, essentially.
Right.
It depends on this, how the system is coupled to its, the coupling of the system to its path is important, of course. But I'm saying that then, after that, what it needs to be compared to, it doesn't seem to be the frequency of the system, but rather the properties of the path itself. So which means, for example, if you have, I don't know, for example, in these conducting experiments, you have these 50 ohm, I guess.
Right.
So it depends on how this, how, at different frequencies, how does this kind of impedance is acting on your system. That's pretty much this, which seems to put the limit on the Markovian approximation.
In the quantum optics, that appears in the quantum optics derivation, in that there's a kappa of omega that's originally inside of the integral.
So
I'm just trying to see where I.
So okay, this is the coupling strength of the.
So the thing I'd say about that is, so I think, in most of the discussions, it amounts to, what are the correlations of these input fields like? You can see from their definition, they depend on both the system and the bath. So they depend on what is the spectral density. So there's a square root of omega there. So that could be a general dependence of the coupling on frequency. It also depends, you see this time dependence, it depends on omega naught. So that correlation function, and there are actually, I was saying, talking about Q, but you could think about, in sufficiently high temperature limit, that you could arrange for those correlation functions to be short as well. And there may be other ways. You'll actually see arguments that justify it on various bases. So it's too narrow to say it's just about the Q, I agree. So the high temperature limit is definitely an important one. There may be others in which you could get that limit to work.
I extremely agree with your comment. Because, for example, in the Segerfeld-Wirzer paper on the quantum jumps, it's actually the environment that makes the system Markovian. So the Hamiltonian is not enough to describe the system.
Yeah.
Because the environment absorbs photons, for example, and puts it into a pointer state. That's why your system loses its memory.
Yeah.
And that makes it Markovian.
That's right. It definitely, it's not a decision you can make just, it's a decision you have to make once you know about the coupling between a specific system and environment. And property, including the properties of the environment. So the properties of those input fields, they know about both the environmental state and the system Hamiltonian.
Yeah, you need three things. You need the system, the path, and the environment.
Yeah.
Like, easier to follow this. Because Slava Belavkin used to say that
any sort of quantum measurement had to be Markovian in order to work. So, you know, we've done all these models where we say we'll have an SLH, we'll have an input, which will be white noise, and there's a Markov interaction here, so you can think of it basically instantaneous for each chunk of the field coming in. And then you say, well, okay, that's of course all an approximation. Let's do something where here's a system, and we've got the electromagnetic field coming in, and we make that as complicated as possible, or whatever the transmission line is. Then we have a detector here, okay, occupying some region D. Okay? So we look at the field that arrives here, and the field can be colored or whatever, and then we start thinking about how we detect this. So if it's the electromagnetic field, say at a point or inside the detector, I assume it's one-dimensional, so we'll just say the Z component. Just following the usual thing, you split this into positive and negative frequency parts. So these involve annihilators only.
Yeah.
I was reading recently Gardner's chapter on this, you know, what actually goes on in the detector. I think it's chapter 8 of the information book, right? So what's the model for this? Well, it's actually, believe it or not, another SLH model where effectively your L distributed, say we're doing the detection at a particular time, it's field here, the annihilator part of the electric field, where your position is just distributed over the detector, and your Hamiltonian is just the usual quantum electrodynamic Hamiltonian, just the sum of the oscillators. So you're somehow sort of sneaking in the continuous SLH because it's parameterized by position coordinates inside the detector. So now when you're talking about detecting what the detector actually detects, you've got a Markov model.
Yeah.
So it's almost like this quantum measurement, where does the apparatus end?
Yeah.
In some senses, where do
So-
you put in the Markov model of the detection?
Yeah, so I think I agree. What I was trying to indicate in the comments at the end, right, is that, you know, I think to have a sensible notion of continuous quantum measurement, you know, I might be closed-minded, but I think what you want is to measure a commuting set of, you know, you're measuring a commuting set of observables.
Yeah.
So in that sense, you know, what's going on here, there's you know, there's got to be something corresponding to that. And I was just arguing that that doesn't necessarily require that the interaction between the thing you're measuring and the field that you're ultimately going to detect has to be Markovian. Right? That's actually a different thing. Right? So it could be possible to construct, you know, commuting sets of observables that correspond to field modes incident on a detector, and yeah, sure, the detector's got some physics that means it's going to detect certain things, and so that there's going to be a commuting set of output. You know, Belavkin called it this QND property of the output fields. Like that would obtain at the detector.
But the QND somehow is following on from the Markovian assumption. It's
So
almost as if you have to you put this in, and the question of where do you put in the Markovian assumption
my claim is you can make it further. My claim is you can make it further away. Yeah, my claim is
and what's the quantum part you're trying to observe. Right?
Yes, that's right. So that, I mean, yes. I mean,
So
there's somehow.
it's purely a modeling problem.
I mean, so this is what I wonder about. I mean, so in principle, I can increase the size of my system, and so I've got some quantum state for some very large system that's then coupled in a Markovian fashion to something that I detect. And so there's always that argument with anything about non-Markovian trajectories. I just haven't made the system large enough. But you know, you might have to make the system pretty large, or to model some of these effects that people can calculate easily in condensed matter physics, you know, where there's some algebraic thing going on, you might not, you know, that might effectively require infinitely large systems. And it just seems counterintuitive to me that there isn't some other way of approaching that in which you don't grow the size of the system enormously.
I've heard people say, yeah, this is actually a Markov system, we just have to make the
It's a
system
big,
whole
big,
universe
yeah,
active.
yeah. But if your system is not readily described by a small number of Lorentzians, it's very, very hard to implement that story, right? I mean, that story is, yeah.
Okay. Any other questions?
Maybe just following on from that, does that really mean that the issue was about approximation of very large Markovian systems by other smaller Markovian systems which are tractable?
So I think that would be, that. I mean, I think that's an alternative way. I mean, if you, so I think that's, so you could go away and say, I don't want a bar of any non-Markovian thing.
I don't believe in
What I want to do, I don't believe. What I want to do is I want to reproduce the physics of this model that we just saw to a higher order in the coupling between the system and the environment by explicitly increasing the size of the quantum mechanical system. And I'm going to demonstrate that by doing that, I can reproduce to greater accuracy some result that's been calculated for that system. So like I'm actually going to go and demonstrate in a specific setting that this program of increasing the size of the system, really gives, really,
and that's a process of making a better and better approximation.
And yeah, what would be really good is to show that by adding systematically more Lorentzians, you can get better and better approximations. And maybe that's, I haven't seen an implementation, that may be out there. I mean, this idea has been written down in various places. There's a paper by Atash Imamoglu that's 20 years old or something, but I haven't seen this implemented in detail in some physical system where you said, yes, we've reproduced really this non-Markovian behavior. So I think it would be interesting to think about examples for that program, because you might be skeptical about my claim that what we really want to do is some fancier version of trajectory theory.
And on that note, which I think is woken us all up on a Friday afternoon, let's thank Andrew for an excellent overview.